all set now. Good morning. And we will finish the lesson from yesterday. And what was remaining was the specifications and testing, if you remember. So we were seeing the production processes, and we stopped here. This was the last slide yesterday. So specifications and testing, we selected the most relevant performance indicators, if we may say so. And we need to take care of how to identify the material and characterize the dimensions of the packages. Then we have a set of mechanical properties like tensile, compression, and drop, resistance to drop, especially in larger packages, can be important, and friction. Then we have barrier properties, permeability to gases and to water vapor, and finally migration of components into food. So here we will see a little bit of methods to identify the material, and then a little bit on barrier properties, how to measure. We have other classes that are fully devoted to migration of components into food. First thing to say, is important to know that in order to get quality results that can be traceable and recognized among parties, it's very important to control and to record the temperature and relative humidity of the environment where the tests are performed of the lab. So a laboratory for testing plastics needs to be with the environmental conditions controlled of temperature and relative humidity. And the typical conditions here in Europe used as standard conditions are 23 degrees C and 50% relative humidity, okay? And our laboratories use this type of equipment that you probably know. We have two thermometers, one dried and the other one wet. And this is the most precise method to measure the temperature and the relative humidity. And then we have a continuous record that can be more or less advanced. But it's important to keep the record of the conditions during the tests. Regarding identification and characterization of the materials, so for plastics we can use some chemical methods, like to check solubility of the material in different solvents, burning and looking into the color of the smoke, the smell of the smoke. These bring us information on the, especially for coatings, we can know what coating is there. And there are a few reactions to specific agents that can be used to verify what is the nature of our material. So this is sometimes used by industry because they are very, very rapid, very inexpensive. They don't need any equipment, just experience, and often industry uses, for example, to check if the polypropylene has a PVDC coating, for example. Then we have methods that use equipment, specific equipment, and you know the infrared spectroscopy is very, very widely used, and we need to have the standard spectras to compare. So we need to have some kind of library of materials to compare with. And the other method that is quite used also, not only to identify but also to characterize, is the calorimetry by differential scanning. Where we are able to determine the glass transition temperature and the melting temperature and other transitions, thermal transitions, that not only allows to identify but also to characterize the thermal history of the material. That can be very important to understand the behavior of the material. And I think that some of you have seen this type of thermogram. And when we heat the material, so in the first cycle we can determine this little step usually identifies the glass transition temperature. Then we may have or may not have a crystallization heating peak. Then we have the melting peak. And when cooling down for materials that can crystallize, we can see the crystallization peak on cooling. And then when we perform the second cycle, we don't see so well the TG. We don't see the TG, and we see the melting peak. So with these two cycles of running, we identified the material by crossing with a table the TG and the TM. Okay? Yeah? No questions? Good. On the mechanical properties, we will not go into detail, but we understand that it's very important during use, handling the material, and during process. It's also important to characterize the material, because the mechanical properties can be modified by using additives, for example. If we have a PVC with plasticizer, or if we compare with a PVC without the plasticizer, we will have mechanical properties completely different. The tensile properties are defined as the resistance the material exerts when it's pulled apart, very simply said. And I'm sure that all of you have seen this type of curves that when we plot the stress, that's the force divided by the area, with the strain, that's the elongation in percentage of the material. And we have, in most materials, we have these two different regions that we designate the elastic region up to the yield point, and the plastic region afterwards up to the point of rupture. Okay, so we say that the materials or the deformation is reversible if we stretch the material up to the yield point. But if we stretch the material up to after the yield point, then the deformation is not reversible any longer, and we will have permanent deformation. And this is the point of rupture. Okay? So this is important to understand and to check which are the conditions that our material is going to be used. For example, if we have a material that is going to be used to palletize, to do a unit load around boxes in a pallet, we want the material to be stretched but to be firmly securing the boxes. So we need to take care of this yield point when we are using those type of materials. And we have materials that are hard and brittle because they have a very high slope here, but the point of rupture is at very low strains. It can be hard and strong, it can be hard and tough, and soft and tough. So these are basically the 4 types of materials. So we use the word hard, strong, or then tough when we have large strains, so large elongations, okay? And we can need, depending on the use, you can need both. Imagine that we are going to the supermarket and we have these plastic bags where we put the things that we bought inside, and then we are holding the bag. We want the material not to stretch, because otherwise we will dragging our groceries. We want the material not to be brittle, okay? We want the material to be hard, but not very tough. Otherwise, it will increase the size. It will elongate. Okay, so depending on the use, we need different characteristics for our material. Okay. Regarding barrier properties, we will spend a little more time in here. First we define permeability as the amount of gas or vapor that crosses the packaging wall of a certain thickness per unit area, per unit of time, and per unit of differential pressure of the gas or vapor that we are discussing. And we can have permeability to moisture, to gases like oxygen, CO2, nitrogen, or other aromas, for example. So we need to understand that if this represents our material, we have a certain thickness of the material, a certain surface area, and we need an external partial pressure of the blues that are our permeant, and we have the internal partial pressure. So we have components that influence our barrier properties: the material itself, the surface area. If we have a larger surface area, the amount of permeant is higher. The thickness of the material. If we have a thicker material, the barrier is better. And we also need to take care of the conditions of temperature, relative humidity, and time. So the measurement conditions regarding the partial pressure difference between the external face of the material and the internal face of the material can be saturation, can be those that exist in the air, or can be close to the real conditions. And it's important that when we report some permeability measurements, we report the conditions that we use to test those materials. And we will see a little later that sometimes industry that sells materials, the way the barrier properties are reported are not complete or completely complete, are not always completed. If I want to measure the permeability to oxygen, okay, what would be the saturation conditions? If I want to measure oxygen, I would put here 100% oxygen and 0% oxygen here. So my driving force is the maximum. Okay? But this is not air conditions, because air conditions is what? What is the concentration, the percentage of oxygen that we have in the air? 21%, right? So if I put here 21% and here 0%, okay, that will be my driving force. It is also correct, but we must say, what have we done? Okay, and so on. These are just examples. And here is a graph reporting the barrier properties of different plastics to oxygen in this side and to water vapor and in the other side. And you see that the units reported are for oxygen, okay, we say the temperature, 23 degrees, and 0% relative humidity. That means we are measuring in dry conditions. And regarding the oxygen, we report in cubic centimeter of oxygen, micron, that's the thickness of the material, per square meter, that's the surface area of the packaging, per day, and per bar. And this bar is the differential pressure of oxygen between one surface and the other surface of the material. So this is a complete, this is the right way of reporting the units for oxygen. As an example, okay? We can use, instead of microns, we can use meters, but in terms of the dimensions is what is supposed to be there. And for water vapor, in this case, we report at we made the measurements at 38 degrees and 90% relative humidity, and usually is more common to report in grams. There is a mistake here, is grams, micron per square meter, day, and bar. Okay, I need to correct there. And we see a little bit of examples of materials, and we see that, as I explained yesterday, the materials that are permeable to oxygen usually are good barriers to oxygen, and the opposite. There is a colleague that's not here today that is working with PVOH that has a very, very good barrier to oxygen, but is very poor barrier to moisture. In fact, is almost soluble in moisture. And therefore, this is the reason, or one of the reasons why we need to combine different materials if we need both barrier to oxygen and to moisture. Okay? Here we see the effect of temperature and relative humidity in this oxygen transmission rate for a film of 20 microns. And we have here in this axis we have the relative humidity, and what can we see that so now we are focusing only on oxygen barrier, and we see that for the polyolefins like low density polyethylene and polypropylene, and also for PET and also for PVDC, okay, polyethylene has a very high permeability, but it does not depend on the relative humidity. Like the PET here in the middle scale, or PVDC that is already in the lower range, so it's a good barrier, and it's a good barrier that does not depend on the relative humidity. So this material keeps the barrier whatever the moisture conditions of use. However, we have, for example, these two green, like AVOH 44%, AVOH 44, it means, remember yesterday I explained that AVOH is a copolymer, so it has two monomers, so 44% or 32% are the percentage of one of the comonomers, okay? So you see that when we have different compositions of the AVOH, we have different behaviors. And this AVOH 32% has a better, even better barrier, but it has a better barrier at low relative humidities. When the humidity goes up, it loses faster the barrier properties to oxygen. Okay? Compared to the 44% AVOH that has, let's say, a not so good behavior, but then at high relative humidities is better. Okay. And the same for nylon, that's a polyamide, like here, polyamide 6 or a polyamide MXD6, which again has a better behavior, but also is influenced by the relative humidity in the same manner. It's clear this? Yeah. Can you figure out from what I explained what is this percentage for each comonomer? Is for the ethylene, yeah? For AVOH with 44% of monomer ethylene, because the ethylene is responsible for the moisture resistance. So if we put more ethylene in the proportion, we decrease the barrier, but we keep the resistance to moisture. Okay? Okay, and in this other graphic here, we can see similar things. It's a film, multi-layer film with polyethylene and polyamide, and we have the experimental data at different temperatures when the relative humidity or the film was dry. And we have also the measurements at the same three temperatures, but where the relative humidity is 100%. Okay, so we see that the permeability increases. Okay, so the barrier decreases, and the effect of temperature is higher than the same effect when the material is dry. So this is, to summarize, it's very important to have the conditions defined. To moisture, how can we measure the permeability? In this case, to moisture, we have some simple tests like these cups where we put the material in here. We put inside some material that is hygroscope, or we can also put water, and we follow the weight gain or the weight loss with time, and with the slope then we can calculate the permeability. But this is a very inexpensive method, but it works only for high range materials. For materials that are good barriers, so this method cannot be used, and we have methods that are more automatic with sensors like infrared sensors, and that are able to measure low quantities that cross the film. For the oxygen, we can have also different types of methods. This is equipment, both of those are quite old, but still working, and we use for oxygen a colorimetric sensor. So it's a sensor that can detect the molecules of oxygen, or is a specific, or we can use a sensor that measures pressure, and in this case can be used for any gas like oxygen or CO2 or even nitrogen, because it senses, it measures the pressure increase on the side of the cell. More recently, there is this sensor based in luminescence. Not sure if it is very clear. We can, oh well, this is a bottle, a glass bottle with a cork. You can recognize that. We have here this little pink dot that has a material that is reactant to luminescence, and we have then a sensor that is attached here, and it can measure the increase of oxygen inside the bottle. So this is a useful method when we want to measure a lot of replicates, because this type of equipment can only be used for two or three, depending on the constructions. This only for one, this for two. We have another one for three with three cells, but nevertheless is a small number of replicates that can be measured each time. For bottles and corks, we want to measure 20 or 100 or things that are a much higher number, so it is not costly possible to use this method. Here are some examples of specifications that I found in the industry, and this is to illustrate, and these are real cases, so it's not invented by myself, where in some cases where the reporting on the material specifications sheet, on the technical sheet, the information on the barrier is not complete. So for example, here they say that the material has a water vapor permeability of 1.6 in grams per square meter per day, and they don't say what at what temperature nor at what partial pressure difference the measurement, if it was saturation or air or real conditions, so it's not correct. Here for the oxygen, okay, they say the temperature, they say the relative humidity, yeah, but what is missing here? The pressure difference, the partial pressure difference of oxygen used in each, so the driving force, okay? And this is the case where, so all of this is wrong, and then we have here good examples, okay? It says, no, this is not okay also. There is something missing here. Can you figure out? Is the thickness of the material, okay? So we can accept, because if this is a specification for a certain material, okay, we can assume that it was for the thickness of that material, but it's not always the case. But nevertheless, the thickness should be here. But they state the methods, the standard, so it's much better, and this is completely not good, okay? And one problem that is commonly referred by food industry is that the temperature of measurement that the suppliers, the packaging suppliers present are not the use temperatures, especially on fruits and vegetables area, that are typically sold at refrigeration temperature. And the permeability specifications are not reported or are reported at 23 or 38 and not at the use temperature like 10 degrees or so. So here is a balance between what is need to be performed as a standard and what must be performed as a useful measure for the user of the material, okay? So it depends, okay? Okay, so this ends the plastic section. I want to know if everything is clear, if you have any question that you want to put now.